Welcome back, traveler of the stars. Tonight, we're going to look farther than ever before, beyond galaxies, beyond clusters, into the edge of what we can see. This is the observable universe, the cosmic horizon that defines how far our eyes, telescopes, and imagination can reach. It's not just a place filled with stars and galaxies. It's a window into time itself, stretching across billions of years, showing us the universe as it once was. So, get comfortable. Let your thoughts drift into the quiet of space. And let's begin our journey through the observable universe, the greatest view humanity has ever known. The observable universe is everything we can see, measure, or detect from Earth using our eyes, telescopes, and instruments. It doesn't mean it's all that exists, just the part of the universe that light has had enough time to reach us from since the beginning of time. When we look up at the night sky, we're actually looking back in time. Every point of light is a message from the past, traveling through space for billions of years before it finally reaches us. Because light travels at a fixed speed, about 186,000 miles per second, we can only see as far as light has had time to travel since the universe began, around 13.8 billion years ago. But because space itself has been expanding all that time, the farthest objects we can see today are now about 46 billion light-years away. That distance marks the boundary of what we call the observable universe. To imagine what that means, picture the universe as a vast, stretching balloon. You are sitting on the surface of that balloon, and as it inflates, every point on the surface moves away from every other point. The farther something is from you, the faster it appears to move away. That's what's happening with galaxies. The universe is expanding, and distant galaxies are being carried away by that expansion. The observable universe is like the part of the balloon you can still see before it stretches too far for light to reach you. Beyond that edge, space continues. But light from there hasn't had time to arrive yet, so we can't observe it. The size of the observable universe is staggering. It stretches roughly 93 billion light-years across, containing all the galaxies, stars, planets, gas, and dust that we can detect. It's filled with over 2 trillion galaxies, each with hundreds of billions of stars. Many of those stars likely have planets orbiting them, meaning there could be more planets than grains of sand on all the beaches of Earth. Yet, as large as it is, the observable universe might be only a tiny part of the whole universe, like a small bubble inside something much, much larger. When we observe distant galaxies, we're not just seeing how they look now, we're seeing them as they were billions of years ago. A galaxy that's 10 billion light-years away appears to us as it was 10 billion years in the past, because its light took that long to reach us. This means the farther we look into space, the deeper we peer into the history of the cosmos. Astronomers often say that telescopes are like time machines. By studying galaxies at different distances, we can trace how the universe has changed from a hot, dense cloud of energy after the Big Bang to the complex cosmic web we see today. At the very edge of the observable universe, we reach the cosmic microwave background radiation, or CMB. This faint glow fills all of space and is the oldest light we can detect. It was released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could travel freely for the first time. Before that moment, the universe was like a thick fog of particles and radiation that constantly scattered light. When it finally cleared, the first light began its long journey through expanding space, and some of that light is still reaching us now. The CMB is like a baby picture of the universe, a snapshot of what it looked like when it was just starting to take shape. It's not bright. It's microwave radiation, which means it's invisible to our eyes, but can be detected by special instruments. When scientists mapped it, they found tiny temperature differences across the sky, only millionths of a degree apart. Those tiny variations represent the earliest clumps of matter that would one day grow into galaxies, stars, and planets. Without those slight, uneven spots, gravity wouldn't have had anything to pull together, and the universe would be an even, empty fog forever. One of the most amazing things about the observable universe is that no matter where you are in it, it looks roughly the same in every direction. This doesn't mean everything is identical. It just means that on a large scale, the universe has no special center or edge. If an alien civilization lived 10 billion light years away, their observable universe would also stretch about 46 billion light years in all directions from their point of view. They'd see much of the same pattern of galaxies, though arranged differently because their position is different. This means that every observer in the universe sees their own version of the observable universe, centered on themselves. The observable universe is defined by time as much as by distance. Because light takes time to travel, the limit of what we can see grows slowly as the universe ages. Every second that passes allows light from a little farther away to reach us. That means our observable universe is constantly expanding, not just because of cosmic growth, but because more of it becomes visible over time. However, there's also a limit to how much more we'll ever see. As dark energy continues to accelerate the universe's expansion, distant galaxies are being carried away faster and faster. Eventually, their light will no longer be able to reach us, even if we wait billions of years. In the far future, many of the galaxies we see today will fade from view entirely. Their light will stretch out so much that it becomes undetectable. Only the galaxies of our local group, like the Milky Way and Andromeda, will remain visible. To distant future observers, it may appear as though they live in a small, lonely pocket of space, unaware that a vast universe once surrounded them. This thought shows how fragile and precious our current view of the cosmos truly is. We live in a special time when we can still see the universe in its full glory. The discovery of the observable universe wasn't immediate. It took centuries of observation and technological progress. Early humans thought the stars were tiny lights in a small dome above Earth. Ancient astronomers like Ptolemy believed the universe was a set of spheres, with Earth at the center. It wasn't until the 16th and 17th centuries that scientists like Copernicus, Galileo, and Kepler showed that Earth was just one planet orbiting the Sun, and the Sun was one star among billions. When telescopes became more powerful, we began to see that stars were grouped into galaxies, and those galaxies stretched far beyond what we once imagined. By the 20th century, astronomers like Edwin Hubble used powerful observatories to measure how galaxies move. He discovered that galaxies farther away are receding faster, leading to the realization that the universe itself is expanding. That discovery changed everything. Suddenly, we understood that the cosmos had a beginning, the Big Bang, and that it has been growing ever since. The observable universe is a record of that growth, a window into the story of how everything came to be. Even today, as we build more advanced telescopes, like the James Webb Space Telescope, we continue to push the limits of what we can observe. The Webb telescope allows us to see galaxies that formed just a few 100 million years after the Big Bang. Each new observation fills another piece of the cosmic puzzle, helping us understand not only where we are in space, but also when we are in time. We are observers, living in a tiny corner of a vast, ancient universe, able to look back nearly to its beginning. The idea of an observable universe also raises deep philosophical questions. If we can only see a part of the universe, what lies beyond? Is there more of the same? More galaxies, stars, and dark matter? Or does the universe end abruptly? Most scientists believe the universe extends far beyond what we can see, possibly infinitely. But since light from those distant regions hasn't reached us yet, we can't be sure. It's like standing on a small island surrounded by fog. You know the ocean continues beyond what you can see, but you can't tell how far it goes. What's truly fascinating is that the edge of the observable universe isn't a physical wall or barrier. It's not something we could reach, even if we traveled at the speed of light. It's simply the point beyond which light hasn't had time to reach us yet. And as the universe expands, that horizon keeps changing. The universe is like a story still being told, and we can only read the chapters that have already arrived. When we talk about the observable universe, one of the most mind-bending ideas is how it connects space and time. Every distant object we see represents a different moment in the past. The farther away it is, the older the light we're seeing. When you look at the moon, you're seeing it as it was about 1.25 seconds ago, because that's how long light takes to reach us from its surface. Sunlight takes about 8 minutes to reach Earth, so every time you look at the sun's glow, Never directly, of course. You're seeing it as it was 8 minutes in the past. Now stretch that idea outward. Light from the nearest star outside our solar system, Proxima Centauri, takes over 4 years to get here. When we look at it, we're seeing that star as it was 4 years ago, not as it is now. As we move farther out into the universe, the delays in time become enormous. A galaxy 10 million light-years away shows us what it looked like 10 million years ago. A galaxy 10 billion light-years away shows us what it looked like when the universe itself was still young. In a way, the entire sky is a timeline written in light, where every star, cluster, and nebula is frozen in the moment it sent its light toward us. By reading that light, astronomers can trace the story of cosmic evolution, the birth of stars, the formation of galaxies, and the expansion of the universe itself. The speed of light is not just a limit, it's also what makes the concept of the observable universe meaningful. Nothing can travel faster than light through space. This means there's a cosmic horizon, a maximum distance beyond which we'll never be able to see or communicate, no matter how long we wait. Space itself is expanding faster than light can cross it at those distances, stretching galaxies away from us so quickly that their light can never reach us. Those regions are beyond our cosmic horizon, forever invisible, even though they exist. This creates a fascinating picture. The universe is much larger than what we can observe, maybe infinitely so. But the observable universe is like a personal bubble around each observer, limited by how far light has traveled since the beginning of time. That bubble is about 46 billion light-years in radius for us, but for an alien civilization somewhere else, their bubble would also stretch 46 billion light-years in every direction from their location. The universe has no true center. Every point can consider itself the middle of its own observable sphere. Inside our observable universe, we can detect structures on unimaginable scales. Galaxies gather into clusters. Clusters form superclusters, and superclusters are woven into filaments that stretch across hundreds of millions of light years. Between those filaments lie immense voids, regions almost completely empty of galaxies. Together, they form what astronomers call the cosmic web. A structure that looks a bit like a three-dimensional spider web or a network of glowing threads. This web is the largest known pattern in existence, and it shows how matter has been shaped by gravity since the beginning. Each filament in the cosmic web is made mostly of dark matter, the invisible material that provides the gravitational framework for galaxies to form. The bright points along the filaments are galaxies, like dewdrops along a strand of silk. If you could step back far enough to see it all at once, you'd see a vast network of glowing threads, stretching in every direction, connected by bridges of light, and surrounded by dark, empty spaces. This structure gives us a glimpse of how the universe grew from the tiny ripples we see in the cosmic microwave background to the grand cosmic architecture we see today. What's even more remarkable is how consistent this structure is at every scale. When scientists measure how galaxies are arranged across billions of light years, they find patterns that match the predictions of the Big Bang model. This means the laws of physics have been the same everywhere in the observable universe, from the smallest particles to the largest clusters of galaxies. It's a reminder that the same basic rules govern everything from the atoms in your body to the stars at the edge of time. The light from distant galaxies doesn't just tell us how far away they are, it also carries the signature of how the universe is expanding. As space stretches, it stretches the light traveling through it. This effect is called redshift, because the wavelength of the light becomes longer and shifts toward the red end of the spectrum. The greater the redshift, the faster a galaxy is moving away, and the farther back in time we're seeing it. Measuring redshift allows astronomers to determine both the distance and the age of distant cosmic objects, building a kind of 3D map of the universe's history. At the largest scales, the universe appears to be expanding uniformly, but on smaller scales, gravity pulls matter together. This is why galaxies can form and stay bound even while the space between distant galaxies continues to stretch. The balance between expansion and gravity is what shapes the observable universe we see today. For billions of years, gravity worked to gather matter into stars and galaxies, while dark energy worked to push them apart. The result is the vast, dynamic cosmos that surrounds us. A place both structured and ever-changing. The observable universe is full of light, but most of it is invisible to our eyes. Human vision can only detect a tiny portion of the electromagnetic spectrum, what we call visible light. But space is also filled with radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. Each type of light reveals different aspects of the universe. For example, radio waves can pass through clouds of gas and dust, showing us what's hidden inside. Infrared light reveals the heat from stars forming deep inside nebulae. X-rays show the hot gas swirling around black holes. And gamma rays reveal the most energetic explosions in the cosmos. Modern astronomy uses all these wavelengths together to build a complete picture of the observable universe. Space telescopes like Hubble, Chandra, Spitzer, and the James Webb each observe in different parts of the spectrum. When their images are combined, we can see the universe in ways no single instrument could ever show. It's like hearing a symphony instead of just one note. The full beauty of the cosmos emerges when we combine all the information light carries. One of the most fascinating discoveries from observing the universe in multiple wavelengths is that it looks very different depending on what kind of light you use. A galaxy seen in visible light might appear calm and graceful, but in X-rays, it could be blazing with hot gas from supernova explosions or black hole activity. In radio waves, it might reveal vast jets of charged particles shooting out from its core. Each form of light tells a different part of the galaxy's story. By studying all this light, astronomers have been able to estimate the contents of the observable universe. Only about 5% of it is normal matter, the stuff that makes up stars, planets, and living things. Around 27% is dark matter, which we can't see, but can measure through its gravitational pull. The remaining 68% is dark energy, the mysterious force causing the expansion of the universe to accelerate. That means almost everything we can observe is made mostly of things we can't directly detect. The visible stars and galaxies are just a small fraction of what's truly there. Even so, the part we can see is filled with beauty and wonder. Within our observable universe, there are an estimated 24 stars. That's a 1, followed by 24 zeros. Many of those stars have planets, moons, and possibly life. Somewhere out there, other civilizations might be looking back toward us, seeing our galaxy as just one faint glimmer among countless others. To them, our entire Milky Way would be a small dot of light, perhaps not so different from how we see distant galaxies. The observable universe is not only immense in space, but also in time. It holds the record of everything that has ever happened since the beginning. When we look at galaxies far away, we're watching the universe's childhood and teenage years. When we look nearby, we see it as it is now. Together, those views form a cosmic biography that stretches across billions of years. Every photon of light that reaches us carries a story of birth, death, and change on the grandest scale imaginable. To truly understand the observable universe, we have to imagine what it looks like from a cosmic point of view. If you could somehow zoom out far beyond our galaxy, past the Milky Way, past the local group of galaxies, and beyond the enormous Virgo supercluster, you would begin to see that all galaxies form part of a larger pattern. You'd notice that space isn't empty, but filled with filaments of matter stretching across unimaginable distances. Between these filaments lie huge, dark voids that are almost entirely empty. The overall appearance would be something like a sponge or a web, glowing with clusters of galaxies at the intersections. That's the structure of the observable universe on its grandest scale. If we could visualize the entire observable universe as a sphere, the Earth would sit roughly at the center, not because it's special, but because that's where we're observing from. The outer surface of that sphere represents the oldest light we can detect, the cosmic microwave background. Everything inside that sphere is part of our visible cosmos, stretching across 93 billion light years from one side to the other. Within it, there are hundreds of billions of galaxies. And inside those galaxies are billions of stars, planets, and possibly countless forms of life. Yet, despite its size, this visible portion is only a fraction of the whole universe. Beyond it lies the unobservable universe, the part that light hasn't had time to reach us from yet. One of the most fascinating aspects of the observable universe is that its size isn't just determined by how long light has been traveling. It's also shaped by how space itself stretches. This can be confusing because when we say the universe is 13.8 billion years old, you might think that the farthest we can see is 13.8 billion light years away. But that's not true. Because space has expanded during those 13.8 billion years, the actual distance to those early galaxies today is about 46 billion light years. In other words, the light we see from the early universe started its journey when everything was much closer together. But while it was traveling, space kept expanding, carrying those galaxies farther and farther away. This stretching of space is also why distant galaxies appear to move away from us faster than light. It's not that they're moving through space faster than light. It's that the space between us and them is expanding. According to Einstein's theory of general relativity, there's no limit on how fast space itself can stretch, only on how fast objects can move through space. This expansion means that the more distant a galaxy is, the faster it appears to be receding. Beyond a certain distance, known as the cosmic event horizon, the expansion of space carries galaxies away faster than light can catch up, so their light will never reach us. Those regions exist beyond our observable limit, forever hidden from our view. When astronomers map the observable universe, they often use something called a light cone to represent what we can see. Imagine shining a flashlight into the night sky, but in reverse. The light from the universe shines toward us, forming a cone that narrows to a point at Earth. The tip of the cone represents the present moment, and as you look farther back along its length, you're moving deeper into the past. The widest part of the cone represents the earliest observable time, when the universe first became transparent to light. Everything that falls within this cone is part of our observable universe. Everything outside it is beyond our reach. To study this vast structure, astronomers use large-scale surveys that map millions of galaxies across space. Projects like the Sloan Digital Sky Survey have created detailed three-dimensional maps of the universe, showing how galaxies cluster together into filaments and walls. These maps reveal that galaxies aren't spread randomly, but follow clear patterns, like cosmic fingerprints left by the early universe. The arrangement of galaxies still carries the faint echoes of sound waves called baryon acoustic oscillations that rippled through the hot plasma of the early cosmos before light could travel freely. By measuring these patterns, scientists can calculate how the universe has expanded over time and how dark energy has affected its growth. The observable universe also tells us about the limits of what we can know. Even though we can detect galaxies billions of light years away, there's a point where we simply run out of light to observe. Beyond the cosmic microwave background, the universe was too hot and dense for light to travel freely. That means we'll never see directly into the first few 100,000 years after the Big Bang. However, scientists can still study that period indirectly by observing the distribution of matter, radiation, and cosmic neutrinos, ghostly particles that rarely interact with anything but were created in abundance in the early universe. Some researchers are exploring the possibility of using gravitational waves to peer even farther back in time. Unlike light, gravitational waves are ripples in the fabric of space-time itself, and they can pass through matter without being blocked. If we could detect primordial gravitational waves produced in the very first moments after the Big Bang, they could reveal what the universe was like before light even existed. That would extend our observational reach beyond the current limits of the observable universe as defined by light. Our understanding of the observable universe is constantly improving because technology keeps advancing. The James Webb Space Telescope, launched in 2021, allows astronomers to see galaxies that formed less than 300 million years after the Big Bang. It uses infrared light to look through clouds of dust and detect faint objects that older telescopes couldn't see. Webb's observations have already challenged some of our assumptions, revealing galaxies that seem to have formed earlier and faster than expected. These findings force scientists to refine their models of how the universe evolved, showing that even after decades of study, there's still so much to learn. Another remarkable instrument is the upcoming Nancy Grace Roman Space Telescope, designed to study dark energy and map large portions of the sky in incredible detail. Together with telescopes like Euclid and ground-based observatories, it will help scientists measure how the universe has expanded and how galaxies have formed and changed over time. The more precisely we can measure the structure of the observable universe, the better we can understand the invisible forces shaping it. When we think about the size of the observable universe, it's easy to feel small or insignificant. After all, our entire solar system is just a tiny dot within the Milky Way, and the Milky Way itself is only one of trillions of galaxies. But there's also something beautiful about that perspective. Despite the immensity of the cosmos, we are able to comprehend it, measure it, and even trace its history. The atoms in our bodies were forged in stars that lived and died billions of years ago. And now those same atoms are part of a species capable of looking back to the dawn of time. The observable universe, in that sense, isn't just a physical region. It's also a story of awareness. It's the record of how light, matter, and gravity interacted to create a universe capable of seeing itself. When you look up at the night sky, you're not just seeing stars. You're witnessing the grand timeline of existence unfolding before your eyes. Each point of light is a window into another era, a glimpse of a chapter written billions of years ago, still traveling across space to reach you. The more we learn about the observable universe, the more we realize that our ability to see it is fleeting. The accelerating expansion driven by dark energy means that the most distant galaxies we can observe today will eventually disappear beyond our horizon. Future generations may live in a universe where most of the cosmos has faded from view. They'll see only the nearby galaxies, unaware of the vast universe that once surrounded them. That's why our time in cosmic history is so special. It's a moment when the universe is still open to us, when we can still look across its full, breathtaking span and trace its origins. As we continue to explore the observable universe, it becomes clear that every piece of information we gather is like a snapshot from the past. Because light takes time to travel, the farther we look into space, the further back in time we see. This means that telescopes are not just tools for looking outward. They're also time machines that allow us to witness the universe's history unfold. When we observe the Andromeda Galaxy, we see it as it was about 2.5 million years ago. When we study galaxies billions of light years away, we're seeing them as they were when the universe was still in its infancy. In this way, the entire observable universe becomes a kind of cosmic archive, preserving the story of everything that has ever existed. The light from the most distant objects is stretched as it travels through expanding space, turning from visible light into infrared and even microwave radiation. This process is known as redshift, and it's one of the main tools astronomers use to measure distance and time in the universe. The greater the redshift, the farther away and older the object is. Redshift doesn't just tell us how far something is, it tells us how much the universe has expanded since the light left that object. This stretching of light gives scientists direct evidence for the ongoing expansion of space itself. Redshift measurements, combined with precise observations from telescopes like Hubble and Webb, have helped create a detailed map of how galaxies are distributed throughout the universe. These maps show that galaxies form enormous structures called superclusters, which contain thousands of galaxies bound together by gravity. Beyond that scale, these superclusters connect into the cosmic web, an enormous network of filaments made up of galaxies and dark matter. Between these filaments are massive voids, some spanning hundreds of millions of light years, almost completely empty. The pattern of this web gives clues about how gravity shaped matter after the Big Bang, and how dark energy continues to pull everything apart. The cosmic web also tells us something profound about balance in the universe. Matter doesn't spread out evenly. It clumps together where gravity is stronger, leaving empty regions where there's less. This unevenness began as tiny fluctuations in the density of the early universe. And over billions of years, those small differences grew into the large-scale structures we see today. What started as microscopic ripples in a sea of hot plasma evolved into the vast web of galaxies stretching across the cosmos. By studying how these structures formed, scientists can learn about the forces and conditions that shaped the universe's evolution. One of the key breakthroughs in understanding the observable universe came from studying the cosmic microwave background radiation in more detail. Satellites like COBE, WMAP, and Planck have mapped this faint glow with incredible precision, revealing tiny variations in temperature and density. These variations, only a few millionths of a degree, correspond to the seeds of galaxies and galaxy clusters. The CMB isn't just leftover radiation. It's a snapshot of the universe when it was only 380,000 years old. By studying it, cosmologists can trace how matter spread out, how fast the universe has expanded, and even how much dark matter and dark energy exist. The observable universe isn't static, it changes over time. Stars are born, live, and die, releasing energy and matter back into space. Galaxies collide and merge, creating new ones. The shapes of galaxies evolve as they interact with their surroundings. Over billions of years, this cosmic evolution creates the breathtaking variety we see across the sky. Spiral galaxies like our Milky Way, elliptical galaxies filled with old stars, and irregular galaxies that have been twisted by gravity. All are stages in a continuous process of transformation. When we look deep into the universe, we see younger galaxies that are smaller, bluer, and more chaotic. Closer to home, we see mature galaxies that have settled into stable forms. This progression tells us how galaxies grow and change through cosmic time. Even though the observable universe seems incomprehensibly large, it still follows consistent physical laws. The same laws of gravity, electromagnetism, and nuclear physics apply everywhere, from the smallest atom to the largest galaxy cluster. This consistency allows scientists to make sense of the universe using mathematics and observation. It also suggests that the universe is homogeneous and isotropic on the largest scales, meaning that no matter where you are or which direction you look, the universe looks roughly the same. This principle, called the cosmological principle, is one of the foundations of modern cosmology. However, the observable universe also hides mysteries that challenge our understanding. For example, when scientists measure the rate of cosmic expansion known as the Hubble constant, they get slightly different results depending on which method they use. Measurements based on nearby galaxies give one value, while those based on the cosmic microwave background give another. This disagreement, known as the Hubble tension, could mean that there's something missing in our understanding of the early universe. Perhaps dark energy behaves differently over time. Or maybe there are unknown particles influencing cosmic expansion. These questions show that even though we've learned a lot, the observable universe still holds secrets waiting to be discovered. Every new observation brings us closer to understanding how everything fits together, but it also opens new puzzles. For instance, scientists are now using gravitational lensing, the bending of light by massive objects, to map invisible matter in the universe. This technique not only reveals how much dark matter exists, but also how it's distributed. Since dark matter makes up most of the matter in the universe, studying its distribution is essential to understanding the full cosmic picture. When we think about the observable universe, it's easy to focus only on its vastness. But there's another important aspect: the limit of time. The light we see from distant galaxies was emitted billions of years ago. But as the universe expands, that light becomes fainter and harder to detect. Eventually, galaxies beyond a certain distance will become completely invisible. This means that the observable universe isn't fixed. It's shrinking in terms of what we can actually see, even though the real universe keeps growing. Billions of years from now, distant galaxies will have moved so far away that their light will no longer reach us, and future observers will see a much smaller, lonelier sky. Still, in our current era, we're living at a special time. We have the tools and technology to observe nearly the entire history of the universe, from the first light to the present day. We can see how stars formed, how galaxies grew, and how cosmic structures took shape. It's as if we've opened a window to the entire timeline of existence, able to witness how everything began and evolved. For humanity, that's a rare and precious opportunity, a moment when the universe still reveals its full story to those willing to look. The observable universe is a vast and beautiful puzzle. And one of its most fascinating pieces is how everything fits together in both time and space. Every particle, every galaxy, every cluster of stars exists within a structure that has evolved for almost 14 billion years. When we look out into space, we're not just seeing random scattered objects. We're seeing the result of gravity shaping matter over cosmic time. Galaxies group together into clusters, and those clusters connect into even larger superclusters. The result is a cosmic pattern that resembles a three-dimensional web stretching across the universe. Scientists often call this the cosmic web. And it shows that the universe has an underlying order, even in its apparent chaos. At the largest scale, the universe appears uniform. But when you zoom in, you find incredible diversity. Some regions are dense with galaxies, while others are nearly empty. The densest areas form structures called galaxy filaments, where hundreds of thousands of galaxies are linked together by gravity and dark matter. Between these filaments are immense voids that can span hundreds of millions of light years across. These voids aren't completely empty. They contain a few stray galaxies and gas, but they are far less dense than other regions. Together, filaments and voids make up the cosmic web. And by studying this structure, astronomers can understand how the universe evolved from its earliest moments after the Big Bang. Computer simulations of the universe's evolution, such as the Illustris and Millennium simulations, have shown how matter clumps together over time. They begin with tiny ripples in the density of the early universe and let gravity do the rest. Over billions of years, these small irregularities grow into the massive structures we observe today. These simulations match real astronomical observations remarkably well, which means that our understanding of the universe's physics is largely correct. However, they also reveal how much of the universe remains hidden from us. Most of the matter that drives this cosmic web isn't visible. It's dark matter, a mysterious form of matter that doesn't emit or absorb light, but still exerts gravitational influence. Dark matter acts as the skeleton of the universe. Ordinary matter, like stars and gas, gathers around it, following its invisible gravitational pull. Without dark matter, galaxies would not have formed as quickly or held together as strongly as they do. By studying how galaxies move and how their light bends around massive clusters, a phenomenon called gravitational lensing, astronomers can map where dark matter is located. What they found is astonishing. Dark matter makes up about 85% of all matter in the universe. Yet, we still don't know what it's made of. Scientists suspect it could be made of unknown subatomic particles that barely interact with regular matter. But despite decades of searching, none have been directly detected. Alongside dark matter, there's another even stranger ingredient in the observable universe: dark energy. This mysterious force is responsible for the universe's accelerated expansion. Instead of slowing down over time, as gravity would normally cause, the universe is actually expanding faster and faster. This discovery was made in the late 1990 seconds, when astronomers studying distant supernovae noticed that those exploding stars were dimmer than expected. The only explanation was that space itself was stretching at an increasing rate. Dark energy now makes up about 68% of the total energy of the universe, but we don't know what it is or why it behaves this way. Some theories suggest it's a property of space itself, while others think it might be a new form of energy field that fills the cosmos. The combined influence of dark matter and dark energy determines the shape and fate of the observable universe. Dark matter pulls things together, while dark energy pushes them apart. For billions of years, the pull of gravity dominated, forming galaxies and stars. But as the universe expanded and became more spread out, dark energy began to take over, driving galaxies away from one another. Today, the expansion is accelerating, and if it continues indefinitely, distant galaxies will eventually move beyond our observable horizon, disappearing from view forever. The night sky will grow emptier, and the universe will become colder and darker as stars burn out and galaxies drift apart. Even though this sounds bleak, it's also a powerful reminder of how special our moment in cosmic history is. We live in a time when the universe is still bright and full of galaxies to observe. We can look across billions of light years and see the faint glow of creation, the traces of the Big Bang, and the birth of stars and galaxies. In the far future, intelligent beings in other galaxies may not be able to see any of this. To them, the universe will appear as a small, isolated island of stars, with no hint of a greater cosmos beyond. They would have no way of knowing that their galaxy was once part of an immense, interconnected universe. The fact that we can see so far gives us an extraordinary gift: perspective. The observable universe shows us that we are part of something much larger and older than ourselves. The atoms that make up our bodies were once part of stars that exploded long before the Earth existed. The carbon, oxygen, and iron we depend on were forged in the hearts of massive stars and spread across the cosmos through supernova explosions. Over billions of years, that material gathered into new stars and planets, eventually forming everything we know. In a real sense, we are children of the universe, made from its elements, shaped by its forces, and capable of understanding our origins. Astronomers use this understanding not only to explore the universe's past, but also to predict its future. The expansion rate of the universe, combined with measurements of dark energy, allows scientists to simulate how the universe will change over time. If dark energy remains constant, galaxies will continue to move apart at an ever-increasing rate. Eventually, only the closest galaxies, like the ones in our local group, will remain visible. Farther in the future, even the stars will die out, leaving behind cold remnants such as white dwarfs, neutron stars, and black holes. This far-off era is sometimes called the heat death of the universe, a time when everything has reached maximum entropy and no usable energy remains. Yet even this distant fate doesn't diminish the wonder of what we can observe now. The observable universe offers a living snapshot of creation in progress. Every galaxy, every beam of light, and every speck of dust tells part of the same grand story. The story of a universe that has grown from a tiny point of energy into a magnificent cosmic web stretching across billions of light years. The fact that we can measure it, map it, and understand it at all is one of the greatest achievements of human thought. When you look up at the stars, remember that every bit of light reaching your eyes has traveled across time and space to get here. Some of that light began its journey before the Earth existed. It crossed cosmic voids, passed through clusters of galaxies, and bent around invisible structures of dark matter, all so it could arrive at this moment. To look at the night sky is to look back into the deep past of the observable universe, a window through which we glimpse not only where we came from, but also where everything is heading. When we think about the observable universe, it's easy to be overwhelmed by its sheer scale. It stretches roughly 93 billion light-years across, containing trillions of galaxies, each one with billions of stars and planets. Yet, despite its size, the entire observable universe follows a clear and beautiful pattern born from a single, tiny, hot, and dense beginning almost 14 billion years ago. Every atom, every photon, and every bit of space-time we can see came from that single moment known as the Big Bang. Since then, the universe has been expanding, cooling, and forming increasingly complex structures, from simple hydrogen clouds to stars, galaxies, planets, and eventually, life. Our ability to observe the universe is like reading an ancient book, where every page takes us further back in time. The closest stars tell us about the recent past, the galaxies reveal the middle chapters, and the cosmic microwave background shows us the very first page, the birth of light itself. Each observation adds a new piece to the cosmic puzzle, allowing us to reconstruct how everything came to be. But no matter how far we look, there's a limit. Beyond the edge of the observable universe, light has not had enough time to reach us yet. That doesn't mean space ends there. It just means our view does. The universe likely continues far beyond what we can see, perhaps infinitely, filled with regions we may never observe. In a way, the observable universe is like a bubble of knowledge, expanding with time. Every second, more light reaches us from distant corners of space, revealing things that were once hidden. Yet the universe itself expands even faster, pushing some regions beyond our sight forever. This balance between discovery and disappearance makes the cosmos both wondrous and bittersweet. We are living in a cosmic window, a brief era when the universe is still transparent and rich with light. Millions or billions of years from now, much of what we can see today will fade into darkness as galaxies move beyond our cosmic horizon. This window of visibility has given us the chance to understand where we come from. When we study the observable universe, we're not just studying stars and galaxies. We're studying our own origins. The hydrogen atoms in your body were born in the Big Bang. And the heavier elements, carbon, nitrogen, calcium, and iron were forged in the hearts of ancient stars that lived and died long before our solar system formed. When those stars exploded, they scattered their elements across space, which later gathered into new stars, planets, and eventually us. Every breath you take contains atoms that have traveled across billions of years, linking you directly to the history of the universe. This realization changes how we see ourselves. We're not separate from the universe, we're part of it. We're made of the same matter, governed by the same laws, and illuminated by the same light that has traveled across the cosmos for billions of years. The observable universe isn't something out there. It's everything we're part of, everything that made us possible. The fact that we can look up, ask questions, and find answers is one of the most extraordinary things about existence. Out of all the possible outcomes in the vastness of space, consciousness arose, capable of reflecting on its own origins. Even though there's still so much we don't know, what we do know is enough to inspire endless awe. We've learned that space itself can stretch, that light can bend, that time can slow down near massive objects, and that the universe began as something smaller than an atom and grew into something beyond imagination. We've measured the faint afterglow of creation, discovered billions of galaxies, and even found planets orbiting other stars that might harbor life. Every discovery pushes the boundary of the observable universe just a little further, and with it, our sense of wonder. As technology improves, we'll continue to explore deeper into space and further back in time. Future telescopes, both on the ground and in orbit, will reveal galaxies that formed just a few million years after the Big Bang. We'll map dark matter more precisely, understand dark energy better, and maybe even detect evidence of other universes beyond our own. Each step forward will help us refine our picture of reality, showing that the observable universe is not static, it's alive with change and mystery. But no matter how far we go, there will always be a horizon, a limit to what we can see. Beyond that edge lies the truly unobservable universe, an endless expanse that we can only imagine. Some scientists believe it stretches infinitely, while others think it might curve back on itself like a giant sphere. There may be regions so distant that their light will never reach us, filled with galaxies that will forever remain hidden. And yet, the very idea of their existence reminds us of how vast and magnificent reality truly is. In the end, studying the observable universe is not just about measuring distances or cataloging galaxies. It's about understanding our place in the grand story of existence. From the smallest particle to the largest supercluster, everything follows the same cosmic rhythm of creation, transformation, and decay. Stars are born, they shine, they die, and their remains seed new stars and planets. Over and over, the universe renews itself in endless cycles of energy and matter. Somewhere in those cycles, life emerged, and with it, the ability to look back and wonder. So when you stand beneath the night sky, remember that you're not merely looking outward, you're looking backward through time. You're seeing the light of ancient suns, the echo of the Big Bang, and the distant whispers of creation. The observable universe is a bridge between what was and what is, between the infinite and the human. It's proof that even in a cosmos so vast, we are deeply connected to everything around us. The atoms in your body are the same as those that shine in the stars. The light in your eyes is the same energy that fills the galaxies. You are, quite literally, made of the universe itself, and through your awareness, the universe is finally able to see itself. And that, perhaps, is the most beautiful truth of all.